graphite from a natural diamond, which in my opinion at least partly suggests that the device is useless. Evidently, to confirm the genuineness of a diamond, two methods need to be used, which means that the testing device needs to be using, then an UV light torch and perhaps density of the precious stones will need to be measured too for more precise results. Nevertheless, just as I said earlier, graphite, carbon and diamonds are made of carbon atoms, and the only difference is the inner structure of the substance. That's why, just like regular coal, diamonds are supposed to burn well. I decided to run an experiment to test this property. I took a quartz tube and put 3 small diamonds into it and started blowing pure oxygen through it. To make the diamonds burn, I'm heating up this section of the tube with a gas burner, and after that, what's left is just to wait. Sometime later, the temperature reached a critical point, and the first diamond started burning with a highly bright yellow flame, and started looking more like a nugget of scorched metal than a burning substance. The other diamond started burning too, several seconds later. Turns out diamonds in a stream of pure oxygen burn just as well as coal, and just several seconds later, these 3 precious stones vanished without a trace. As a result, no matter how expensive and beautiful a cut diamond is, it can easily be burned, and thousands of euros can be turned into a small amount of carbon dioxide, which costs almost nothing. It's noteworthy that diamonds on Earth were formed out of ancient carbon dioxide, which in the course of a million of years sank from the Earth's atmosphere into various minerals and hydrocarbons, which under the influence of enormous pressure and heat at the depth of half a kilometer turned into one of today's most precious stones on the Earth. Since we have mentioned the so-called carbon circle, let's see how carbon dioxide could form not only diamonds but also entire rock masses from carbon deposits. The thing is, about 4 billion years ago, after our planet cooled off, the young Earth's atmosphere was up to 20% carbon dioxide. That's why it was impossible to breathe on Earth at that time. Because of such a high concentration of carbon dioxide in the air, it dissolved very well in seawater. That's why ancient oceans taste like slightly carbonated water. Along with that, many minerals, for instance minerals containing calcium ions, were washed away from the young Earth's crust. By the way, they reacted well with the slightly carbonated water, in fact just as well as the process of enriching calcium hydroxide solution with carbon dioxide. As a result, the reaction produces calcium carbonate or limestone, and in the course of millions of years,